So let's look at another example of a confidence interval using the independent or two-sample T procedure. So say that we're looking at how long it takes to complete some task, and we want to see if a certain drug maybe improves that task. So this may be a situation where you're working in an environment where people have allergies, so maybe the drug is some sort of allergy treatment, and you want to compare to see if it's really effective or not. So what you do is you set up an experiment where you have some people come in and agree to the procedure, and then some people get a placebo, which looks like a pill that has drug in it, but it really doesn't have any of the medicine in it, versus the other people who probably would get the actual drug or the allergy medication or whatever. So our parameters that we're going to have, we'll let mu sub 1 represent the mean time to complete the task for everybody who could have no drug, be given a placebo. So they're sort of what's called a control group. And then mu sub 2 would be the mean time to complete the task among everybody if they did take the drug. And then what we want to do is sort of estimate that difference, mu1 minus mu2, which is going to be the difference in the mean completion times for all people who were given a placebo versus the actual drug. So here's the output from StatCrunch, and you can tell that it's a 95% confidence interval where the first group was the control group, so those are the ones who had the placebo. The second group is the experimental, or the ones who had the actual drug. And then what we're estimating is mu1 minus mu2, and we're doing it without the pooled differences, or without pooled variances in estimating the mean difference. So the sample mean, if you took the difference in the two y bars, it turns out to be 2.29. Now the standard error, which is a little bit complicated, you can go back to the formula and look at it, but it turns out to be a little bit less than 1. The degrees of freedom is calculated to be 28.8 and so on. So what the software will do is figure out how to handle that to get a t-score. And then when it calculates the lower and upper limits, when it does the subtraction, it gets about 0.366. And when it does the addition, it gets 4.21 or 214. So next, we want to sort of interpret what the lower and upper limit tell us. So the interval, let's just round off to the hundredths digit, runs from 0.37 to 4.21. Now notice that both values are positive. There's not a negative sign sitting in front of the first value, so we know both values are positive. Now if the difference is positive, that tells you the first number is bigger than the second number. So what that tells me is that mu1 is always going to be bigger than mu2 in terms of our estimation procedure. So what I would say is, with 95% confidence, I estimate the mean time to complete the task for people taking the placebo, so these are the ones, remember, who do not have the actual drug, is between 0.37 to 4.21 minutes more than the mean time for those who are taking the actual drug. So what it seems like is that the drug is working to improve the speed with which people are getting the task done, because it takes longer if you don't have the drug, so it takes less time if you do have the drug in your system. And again, this could be like an allergy medication, where if you have the placebo, you're not getting any relief, you feel congested, and everything, and you just don't feel quite yourself. Whereas with the allergy medication, maybe things clear up, you're getting better oxygen intake and stuff, and you're able to work a little bit faster. So in this case, we're seeing that as the time was measured in minutes, and we get this interval that has both a lower and upper endpoint that are positive, and remember that's the answer to this subtraction question, that tells me this first population mean, I think, is at least 0.37 and at most 4.21 minutes more than mu2, which means the task completion time is longer on the placebo than with the drug. Now, just note, if both values had been negative, so if I switched it around, that would give me actually two negative numbers, but it would suggest the second population mean is always larger than the first. Okay, so remember, in everything we're doing in these chapters now, you've got to remember that this is an answer to a subtraction question. Now let's go back and talk about what level of confidence means. We haven't really mentioned what we mean by the term 95% confidence in a little while, so I want to go back and review the concept. Remember, the idea is we're trying to estimate the mean time for the placebo minus the mean time for the drug in terms of task completion times. And what we do is we take a sample, we calculate an interval. We take a sample, we calculate another interval. And we would do this multiple times. And what we really want to do is think about what this term 95% confidence means. Now remember, mu placebo minus mu drug is one number, but we don't know what that number is, and we're trying to predict what that number is. So when we calculate an interval, we're going to get two endpoints. You know, we got 0.37 to 4.21. If I calculated a different interval, it's not that this difference in the population values is changing, but it's those endpoints. So I may get 0.30 to 4.11 next time. And then if I calculated another interval, I may get 0.44 to 4.38 or something. So the idea is, as I take multiple samples and I calculate different confidence intervals, I'm going to get different intervals. And the idea of confidence is 95% of all the intervals I could construct using this method are going to contain what it is I'm trying to estimate. So basically, if we took a large number, say 10,000 different samples is what I'm talking about here, a large number of different independent samples of 40 people, that was the setup, even though it wasn't really mentioned early on, and randomly divided them, okay, into groups of 20 each, I think is what it turned out to be. And we gave one group the placebo and measured time to complete the task, and then gave the other group the actual drug and measured time to complete the task, and then made a confidence interval. Then 95% of all the intervals, right? So 95% of those sort of 10,000 different intervals I could create would contain whatever the true difference of mean times to complete the task for all people using the placebo compared to those using the drug. Okay? In other words, 95% of all the intervals would contain whatever mu placebo minus mu drug actually turned out to be. Only 5% of those intervals would not contain that true difference in mean completion times. And that's what we mean by confidence.